Okay, in the previous videos, I showed you how to do a chi-square test for goodness of fit. We had one sample and we were comparing a distribution, or we were comparing a distribution of uh, one categorical variable with multiple categories to expected counts for that categorical variable, that distribution. Now we're going to look at two other chi-square tests. These are conducted a little differently than the chi-square goodness of fit test, but they work in the same way. The distribution looks the same. All of the inference stuff works the same. Just conducting them is a little different. These are chi-square tests for independence or homogeneity. The good thing is both of these tests are very, very similar. So we need to decide when to use which one. We're going to use the chi-square test for independence when we're looking to see if there is an association or if there's a dependence between two categorical variables within a single population. So if we were looking at something like, we'll do an example here in just a few moments, but we're looking at one single population. We pull a sample and we want to compare the relationship between two categorical variables within that one population. A chi-square test for homogeneity involves two samples. We're looking to see if the distribution of a single categorical variable is the same in two or more different populations. So this would involve two samples from two different populations and measuring counts of the categories for one categorical variable, then comparing the counts in the two populations. We'll show you kind of how this works. In a chi-square test for independence, we need to determine the two variables that we want to compare. So here, this is a table that was set up, and these chi-square tests for independence and chi-square tests for homogeneity will always involve a two-dimensional table with rows and columns. You could have more than three categories or more than two categories, but there's always going to be two different variables, one represented by the columns in the table, one represented by the rows in the table. So we're going to determine the two variables we wish to compare. We're going to select a random sample from a population, or we would randomly assign experimental units to treatment groups. Then we're going to record the values of the two categorical variables for each subject or experimental unit. Now, these observations, these are coming from a survey of our experimental units or our sample participants or our sample, our subjects in a sample. And these are always going to be counts. That means these are always going to be whole numbers. If you try to enter this matrix, we're going to enter this matrix in the calculator when we do the test. If you try to enter it with decimals, it's not going to take it. It's going to give you an error because it's expecting counts for a categorical variable, and it expects that in whole numbers. Then we're going to enter those observed counts in the appropriate cells in a two-way table. So here, it looks like a survey within a single population where we ended up with males and females in our sample, and we were asking about their favorite pet, dogs, cats, or other. And these are the counts where 13 males preferred a dog and 9 males preferred a cat and 4 males preferred other, so on and so forth. This is how we would gather data for a chi-square test for independence. These males and females come from the same population. We're wanting to know if there's a difference between the way, or if there's independence, if there's an association between the gender of a subject and the favorite pet of that subject. That's what we're looking for in this chi-square test for independence. A chi-square test for homogeneity, remember homogeneity means the same. Here we're going to determine the categorical variable. Remember, it's one categorical variable now that we want to compare across two or more populations. We're going to select a random sample from each of the populations or randomly assign experimental units from each population to treatment groups. We're going to record those values. These, again, are our observed counts, variables for each subject or experimental unit. And then we're going to enter the observed counts in appropriate cells in a two-way table. These are going to be our observed counts. Again, this is important because we're going to have to set up another matrix, same dimensions, for our expected counts in a few moments. We'll show you how to do that. This is kind of similar, but here we're comparing a sample of people from Little Rock and their favorite pets and a sample from Memphis, two completely different populations, but seeing, we're going to check when we run this chi-square test for homogeneity to see if there is the distribution between people in Memphis and the people in Little Rock are the same as far as their favorite pets. That's what a chi-square test for homogeneity would do. So let's look at criteria for full credit on both of these. It's going to be the same on both of these, even though there's a slight difference in the way we write our hypotheses and our conclusions. But the criteria are the same as what we've been doing before for hypothesis test. We have to name the test by name or formula. We have to check conditions for inference. We have to write hypotheses, the null hypothesis and the alternative hypothesis. We have to perform calculations, and then we have to write our conclusions in context. Anytime we see a problem that asks for evidence, statistical evidence, or is there statistical evidence, or is there evidence to suggest, then we need to perform a hypothesis test. And if it's to comparing categorical variables, in this way, we could either use the chi-square test for independence or the chi-square test for homogeneity. But we must do all 5 of these things to get full credit. When we look at the chi-square test, with the criteria for full credit, we're going to name the test. If we have one sample, 2 different variables, categorical variables we're comparing, we're going to use a chi-square test for independence. Okay, this is when we have 2 samples. And 1 categorical variable, 2 categorical variables. 1 sample, just getting ahead of myself. 2 categorical variables. Formulas will be the same for both these, so I'll go to that in just a moment. Chi-square test for homogeneity is the name we're going to use if we have 2 samples, 2 or more samples from different populations. And we're looking at the distribution of a single categorical variable. Either one of these you can name with the equation for a chi-square test. And let's go ahead and look at that, find us an image. On your formula sheet also. This is the equation of a chi-square test. And the O means observed and the E means expected. We'll show you what that means in just a minute. Let's see. For either one of these, and I would suggest when you do calculations that you write this down, but this means observed counts. Those are the counts that we recorded in the tables before, okay? The E, we're going to construct a matrix that has the same dimensions. Here we would have enter this as a 2 by 3 matrix in our calculator for our observed counts. We're also going to enter a 2 by 3 matrix for our expected counts. And I'll show you when we do our calculations how to calculate those expected counts. But for each entry, or for each of this part of the sum for the chi-squared value, we're going to enter the observed count minus the expected count for that cell in our table, square that difference, and divide by the expected count. I'll show you how to do that when we get to the calculations here in a few moments. But when we name the test, we're going to either name one of these 2 tests or use the formula. The formula works for both tests. Criteria for full credit, conditions for inference, similar to what we've done in the past. For a chi-square test for independence, remember here we're doing 1 sample, so it needs to be a random sample, or random assignment to treatment groups of your experimental units. Second, this time, all expected counts are greater than 5. So when we can build that expected count matrix, we need to see that all expected counts are greater than 5. Otherwise, we haven't satisfied our conditions for inference. It doesn't matter what our observed counts are. In your observed counts, you can have less than 5 or 5, but you can't have in your expected counts numbers that are less than or equal to 5. And finally, our little n is less than or equal to 10% of big N. Sample size is less than or equal to 10% of the population size. And the great thing about these two tests is they're almost exactly the same. Except for, since we're taking 2 samples here, we need random samples or random assignment to the treatment groups. Both samples in a chi-square test for homogeneity from each population have to be random samples. All the other conditions for inference are the same for both tests. Let's see. Oh, write our hypothesis. We didn't get that one yet. Chi-square test for independence. When we write the null hypothesis, is always going to be that now we're going to, in context, two categorical variables in context are, we're going to have to adjust for each problem, are independent. That means that knowing that one is true doesn't affect the others. Here, when we look at our examples from before, if we were looking at this one, our null hypothesis would be that gender and favorite pet are independent. That would be our null hypothesis if we were running this chi-square test for independence. Our alternative hypothesis, you may already figure this out, 2 categorical variables in context. Or, you probably guessed it, dependent. All that means, if they're independent, we would expect the same proportion of males and females to prefer dogs, cats, and other. And we would prefer the same proportion of people who prefer dogs as to people who prefer cats or to people who prefer other. That's what we would expect. And you'll see how this works out when we create the expected counts. Let's see. Test for homogeneity, chi-square test for homogeneity, or null hypothesis, is going to be that the distributions of, we're going to do the categorical variable in context, are the same for, now, populations. It could be, usually it's going to be 2 populations, but it could be more than 2 populations you're comparing. For populations in context. So again, if we go back to our example we did up here with the table, if we were running a chi-square test for homogeneity for this, we would say that the favorite pets, the distribution of favorite pets for people in Memphis and people in Little Rock are the same. That is what our null hypothesis would look like if we were doing that one. And then our alternate hypothesis is distributions of categorical variables in context are not the same for the populations in context. So those are how we write the null and the alternate hypothesis for the chi-square test for independence and homogeneity. Let's see, let's talk about the calculations. Chi-square test for independence, we are going to calculate degrees of freedom. Show you how to do this in a few minutes on the next 2 slides. we're going to calculate the chi-square test statistic. That's the chi-square value for our samples, or sample in this case in independence, samples in the next one. Then we're going to calculate the p-value. Like before, our calculator is going to do that for us. You're going to have access to the calculator on all parts of the test. Degrees of freedom. Oops. Yeah, that's it for them. That's what I was looking for. Okay, sorry. All right, so now we need to figure out how to do this. This is going to be for both tests. For both tests, we calculate all four of these, and we're going to list all four of these. Make sure when you perform your calculations that you write all four of these on your solutions if you're doing a free response question. So let's talk about how we calculate the chi-square value. That is that formula that we found just a moment ago. Let's go back here and let's do something different here. Thought I had another slide here. Okay, all right. We're going to do the chi-square value and the p-value in a few moments. But right now, we're going to do the degrees of freedom and the expected counts. Let's look at it. Let's talk about how to do that first. Let's move this slide up. I got to delete these because we don't have expected counts yet. Oh, I see what I did. I'm going to duplicate. What in the world? I need to duplicate this slide and move it down. I accidentally replaced one of my slides that I needed here. So instead of this, what we're going to do is figure out how to do the degrees of freedom. And the expected counts. You must show your expected counts when you do these. Degrees of freedom is easy. We're dealing with matrices, and we have rows in our matrix, and we have columns in our matrix. And the degrees of freedom is going to be the number of rows you have minus 1 times the number of columns you have minus 1. So this is 2 rows and 3 columns. The degrees of freedom is always going to be number of rows minus 1 times columns minus 1. And that's your degrees of freedom. That's for either the chi-square test for independence or the chi-square test for homogeneity. So here, our degrees of freedom would be 2 minus 1, or 1, times 3 minus 1, or 2. So our degrees of freedom equals 2. Now your expected counts. Whenever you calculate an expected counts, each cell will have an expected count. Remember, the observed counts have to be whole numbers. The expected counts can be decimals. But the way we're going to get the expected counts is we're going to do the row total. I'll show you what that is in a minute. Oops. Times the column total. Divided by what I call the total, or you added up all the columns or all of the rows, you would get the total number of observed counts in your matrix. So here, if we want this expected value, we're going to multiply the total number here, which is 23, times the total number on this row, which is 22, 26. So 23 times 26, and then divide that by the total in our matrix altogether. So here I have 27 and 26. That's going to be 53. So divided by 53. Row total times column, or sorry, that was column total times row total, same difference, divided by the total. Add up all the cells to get the total. The columns, the first column, first row entry in expected counts is the first row total times the first column total divided by the total. For the cat, the second column in the first row, we would do the second column, which is 19, times the first row, which was 26, and divide that by the total, which was 53. And the next one, we would do the column total, which is 11, times the row total, which is 26, divided by the total, which was 53. Here, second row, first column, we had first column, second row totals. So now 23 times 27 this time, still divided by 53 because that's the whole, that's the column total, or that's the total. Over here, we would do 19. That's the column total times the row total, 27. Oops, goes there. Divided by the total. Here, we would have column total, 11, times the row total, 27, divided by the total. And that's how you calculate your expected counts in a chi-square test for independence or a chi-square test for homogeneity. And you can enter these as decimals in your calculator when we run the test. If we want the chi-square value, then we go back and we look at this. Let's see, I'm going to put a big X squared here. We'll do it like this so we don't have to waste time for that. What we're going to do, now this is going to be, if we go back up here, the observed count minus the expected count, take that difference and square it. And then we're going to divide that by the expected count. So here, this is, I'm going to call this 1, or just call this 1, 2, 3, 4, 5, 6. So to get this, I'm going to get this, it's going to be, I'm going to call it O1 minus E1 squared divided by E1. And then plus, there's 6 of these, right? The observed count in the second entry minus the expected count in the second entry, square that, and divide by the expected count in the second entry. And we're just going to keep doing that 6 times. That's how you get your chi-square value. I'll put some space in there. The chi-square value, if you're looking at the graph, this is what the graph of chi-square distribution looks like, if you remember that. The chi-square value would end up somewhere over here. If this is our chi-square value, I'm going to stretch this down here. That's it. That's the chi-square value. It is between 0, it's going to be a positive number. 0, if if your expected counts and your observed counts all were equal, it would be 0. So it's got to be greater than or equal to 0. But if it falls here, then the probability of getting that chi-square value or greater, if the null hypothesis is true, is equal to the p-value, and it's represented by a shaded area in the tail. Let's see, I guess the border. No, that's not what I want to do. But if we shaded this value here, that would be the p-value. And that's the probability of getting this chi-square value or larger if our null hypothesis is true. The calculator is going to give you the p-value, but I want you to understand what it represents here. And it represents the area under the curve to the right of your chi-square value. This is your chi-square value. And whatever area is to the right of the curve, that is the p-value. And if that p-value is less than your alpha in your hypothesis test, just like it was before, then we reject the null hypothesis and the evidence suggests the alternate hypothesis. And if the p-value is greater than alpha, it means that your chi-square value, the p-value, the probability is greater than the alpha value, the significance level. And so you fail to reject the null hypothesis, and the evidence, there's insufficient evidence to suggest the null hypothesis or the alternate hypothesis. So now let's talk about these conclusions in context. I don't need these anymore. For our chi-square test for independence, we have two cases. If the p-value is less than alpha, or if the p-value is greater than alpha. Again, it's very unlikely that your p-value is going to actually equal alpha. If it does, I'll let you go either way there. If the p-value is greater than alpha, our conclusion is going to be because, and we have to tie the conclusion, we write it, we have to tie it to the p-value. So because the p-value, remember this is different than p in a hypothesis test, so we're going to refer to it as a p-value. You can put the number here. Let's go ahead and do that. Whatever that p-value is equal to in your problem is less than alpha. We'll put your alpha in here. We reject the null hypothesis, and the evidence suggests, this is where you put the alternate hypothesis in context. That's your conclusion if your p-value is greater than alpha. Or sorry, less than alpha. If your p-value is greater than alpha, we're going to say because p-value is greater than alpha, we fail to reject H naught. And there is insufficient evidence to suggest your alternate hypothesis in context. I have to write the alternate in context in these conclusions. Great thing is, these are the same for both tests. Chi-square test for homogeneity and for the chi-square test for independence. Very, very similar to all of the hypothesis tests we've done before. This time we're just doing it with two or more variables in, or two or more populations with categorical variables. So that's part one of your chi-square test. Next, we'll do an example.